Some great examples of building automation systems include climate controls, lighting controls, card access and other security related systems, automated shading and window controls, and fire detection and suppression. These are just some examples. There are many, many, many examples that can be had of building automation systems. Arguably, you could even say that a programmable thermostat in your home is a building automation system. And indeed, we're seeing a lot more home automation systems that have grown kind of as a stepchild out of the commercial building automation system industry. And, you know, the IT side as well. So that's kind of the crux of it. All of these systems have a few things in common. And I think these are the kinds of things that really define what a building automation system is. All building automation systems have some sort of sensors associated with them. Climate controls, oftentimes we're talking about temperature and humidity, air quality sensors, airflow sensors. Fire alarm and suppression, we're talking about the smoke heads that detect fire, detect smoke. Card access, the card readers themselves. Security cameras, the cameras. Lighting controls, everything from occupancy sensors to light level sensors to even just the simple switch on the wall. Those are all inputs into our system. Sensors and inputs are all ways that we monitor real world data. What is happening in the real world that we're trying to control or use as a reference to control something else? Our next step, of course, in system is logic. We have data. We have to decide what we're going to do with that data or what we're going to do as a result of that data. All building automation systems have some logic built into them. Whether this is a logic that is customizable by the user or by a technician, or if it's pre-programmed and what you get is what you get. For example, our thermostats, electronic thermostats at home. Those are kind of they are what you get. There's a certain level of configuration that we can do, but past that, it's only going to do what it's going to do. To fully programmable controllers, the controllers that we use in climate controls specifically are not dissimilar from those used for PLCs. There are some inherent differences, some cost differences, things like that, but when you get down to it, they're very, very similar. And most of those are very versatile, so they can be used for many different applications. Up next, we have real world action. Our building automation system is typically all but useless if we don't have some sort of real world action as a result of the data we're monitoring. Now, of course, there are exceptions to this when we monitor freezer temps or cooler temps for logging purposes, especially when we get into things like the pharmaceutical industry. But for the most part, the data that we collect with a building automation system, we act upon. In a fire suppression system, when we detect smoke, we set off the fire alarm and possibly the fire suppression system in that area. For lighting control systems, when somebody flips the light switch on, hey, we turn the lights on. I know, wild stuff, right? And everything really kind of follows through that in a reasonable quantity of logic. Typically speaking, climate controls are some of the most complex from that logic standpoint. Lighting controls are pretty straightforward and simple. Somebody turns the light on or switch on, we turn the lights on. Turn the switch off, lights turn off. Now, of course, that can get more complicated when we get into presentation modes in commercial buildings, or if we get into theatrical lighting. Those systems are exceptionally complex. And building automation systems are reasonably, you know, we have to have some way to interact with it, some sort of a user interface. If we don't have a user interface, some way for somebody to interact with it, that means anytime we need to make a change, then we're calling in a technician to do that. And that can be fairly ineffective, especially right now with the complexity of the systems and the shortage of technicians, because almost every commercial building you run across, even from as simple as a fast food restaurant to our high-rise skyscrapers and tech giant buildings, all have multiple building automation systems within them. Sometimes they're tied together, sometimes they're not, sometimes they're completely separate. So having to require a technician to come in every time even a minor change like a set point needs to be changed is really impractical. Now, there are some services that have been starting up in the last handful of years where third-party companies will do exactly that. They will monitor your system for you from a remote standpoint and effectively take care of it. Send you notifications when there are alarms, or even just send out a technician when there are alarms to deal with whatever problem you're having. Those are growing in popularity, but I wouldn't say they're the most common solution as of yet. Any questions so far? Sorry, Zoom and I don't always get along. So I'm trying to get to the chat. All right. So for this workshop, and typically most of our best workshops, as far as the BAS side goes, we'll be focusing on climate controls. So why? Why do we focus on climate controls? Lighting controls are easier. They're much more simple. They're easier to teach to students because everybody's familiar with lights. You turn the switch on, the light turns on. That type of thinking. Occupancy sensors. Somebody walks into the room, the lights turn on. Or somebody leaves the room for a certain amount of time and the lights turn on. Really simple and straightforward, right? Well, that's opportunities to learn for our students to learn left on the table. Why not use card access systems, security cameras, things like that? Those are super high point right now as far as the world that we live in. More and more companies are installing these types of systems. They're getting more advanced, better cameras. Surveillance is becoming a much more key topic, especially when people are building new buildings. So why don't we talk about them? Well, again, they're actually pretty simple to set up. Don't get me wrong. I'm not saying that these systems and lighting control systems aren't complex, because they definitely are, or at least can be. And there are many things that we can learn from them. But when we get down to it, they're really basically configurable systems. The lighting controls, you're associating an occupancy sensor with a room, you're associating a light switch with that room, you're associating a set of lighting outputs, whether it's relays or light fixtures or whatever. It's all just kind of associating them together as a group, and we already know how they're going to work together. Card access and security cameras are very similar. Yeah, you've got a lot of details with security cameras as far as focusing the camera, where to point the camera, things like that. But from a setting up the system standpoint, yeah, there's a whole lot of wiring involved with card access. Getting to be a little bit less so now that we're doing a lot more with Ethernet cabling. But from a initial setup standpoint, there's a lot of drop-down menu, click this, click that, knowing how to use company X's software. So again, a lot of learning opportunity left on the table. Climate controls very frequently are the most complex because they have to be the most versatile, because climate controls in the Midwest operate differently than climate controls on the East Coast or the West Coast, North versus South, North America versus Asia versus Europe. We all have different codes that we're following as far as certain procedures go, fire alarms, shutdown, energy codes, things like that. We are getting more on the same page, but we're far from standardized at this juncture. And groups like ASHRAE and the International Energy Code committees are trying to standardize things more, but as you well know, those types of things take time. And technology sometimes outpaces the changes that we see. So we may have newer technology that we could apply that just doesn't show up in any standards yet. So we have to find some way to prepare our students for exactly those situations. So, are we there yet? I can hear it. It's okay, I understand. Questions so far? You'll hear me ask that a lot. That's a holdover from, you know, life in an actual classroom, I think. I like questions, I like feedback. So everything making sense so far?
And just so you know, Robert, I'll be monitoring the chat, so
Awesome.
you can ask
Thank you,
questions
Ted.
as they come in.
Fantastic. All right, we continue forward. Maybe. There we go. So, right. We're going to talk a little bit about climate control systems. I know we have a lot of programs within the BAS network that are based on or developing out of HVAC programs. But just because that's most of them doesn't mean it's nearly all. I know we've got a number of programs based more in renewable resources and things like that. So we really kind of need to define some of what we're talking about. So the basis for the project we are working on today is a variable air volume system, okay? And that means exactly what it says. We're going to vary the amount of air that we put into a building related to the load in the building. These systems typically are constructed of a handful of major components and then a whole lot of small components. We can start our journey at our source for heating and our source for cooling. And yes, for those in HVAC, I know there's no such thing as a source for cooling. It's just a heat sink, and you're right. But we start off at a chiller plant and boiler plant, or hot water and chilled water plant. Sometimes these are separate entities, sometimes they're the same entity. But either way, they consist of a handful of usually fairly large equipment that's whole goal in life is to make hot water or steam and chilled water that we circulate using pumps throughout the building to distribute or absorb heat at our destination points. The largest users of both hot water and chilled water are typically going to be, or individually largest users, are typically going to be what we call air handling units. Air handling units are basically an outsized version of the furnace that you have at home. Commonly, you know, they have varying degrees of complexity. I have seen units that are, you know, almost identical to a residential furnace. I've seen units that are large enough that you couldn't fit them inside the building. You know, 60, 80 feet long and 30, 40 feet wide, 20 feet tall units. So the complexity of these units is extremely variable, depending on the task that they're going to perform. But commonly, they're going to have one or two fans or fan setups, one on the supply side, one on the return. These usually have an ability to vary the speed or vary the volume of air that they're pushing. Sometimes it's single fans for each of these. Sometimes it's multiple fans in what's referred to as a fan wall setup, but not always. They'll often have, almost all of them have some sort of filtering material, anything from your basic, you know, MERV 13 type filters all the way up through and past HEPA filters, multiple filtering banks, depends on the project.
Did you send a letter to McKinley?
We also have heating and cooling coils. These are what utilize our hot water and chilled water, or our steam, whatever our building is producing, to increase or decrease the amount of heat in the air that we're circulating throughout the building. Now, typically in a variable air volume system, we try and distribute cold air or cool air as our standard. You know, something around 55 degrees to 65 degrees, depending on the outside air climate, heat load in the building, et cetera, et cetera. We also usually have some sort of outside air and return air, relief air type dampers that operate in sequence to maintain minimum fresh air requirements for the building, maintain safe quantities of CO2, volatile organic compounds, things like that. And also maintain to some level the pressure within the building, trying to maintain a slightly positive pressure. Because as you all, I'm sure, know, if you can maintain a positive pressure in your building, it's much easier to control the climate within the building. It's easier to keep it clean, all of those types of things. So they may also include systems like humidifiers or dehumidifiers. Desiccant wheels are common in our area of the Midwest, or my area of the Midwest. Heat exchangers, which can be a combination of dehumidification and energy savings, so that we're, you know, in the air that we're exhausting from the building, we're trying to pull out as much of that energy that we placed into that as possible. You can also have airflow measuring stations. These are much more common now than they were 15 years ago, 10 years ago. And UV lights have become hugely popular within the last year. I can't imagine why. So, and other sanitizing systems, ozone generators, you name it. And, you know, it's kind of one of those everything but the kitchen sink deals in some of these air handling systems, especially when you get into very specific applications like hospitals, like clean production rooms, like pharmaceuticals. The more specified, or the more, the tighter the conditions that need to be held, the more things they tend to place into the air handler. And accordingly, the more complicated our task becomes when we go to program them and set them up. Of course, they do make factory controlled air handlers, very similar or somewhat similar at least to our packaged rooftop units, with varying sets of capabilities, oftentimes factory controls that just have a network interface, and the company that produces them, Trane or Dakin or Mammoth, for example, are all three companies that make large air handling units that come with factory controls pre-set up. So what you get is what you get. Or they can come with no controls at all and everything has to be installed by a technician. Well, I'll be honest, those are my preferred tasks to deal with. Just from experience, they're easier to get to perform the way I want them to. But it's been a while since I've had to deal with one that actually had factory controls. So that may have changed in the last few years. I kind of doubt it. Anyway, so our air handlers supply the main conditioned air that we pass into the building. They're kind of that major processing. They deal with the large volumes of air to take care of a portion or an entire building. At the end of those runs, we have to have zone controls. For those of you who are sitting in your labs, sitting in a classroom, those are frequent locations for a specific zone control. And this is where our VAV box or our air terminal unit lives. And for our workshop, these are really the hero because they have a huge quantity of complexity, but they don't have a huge quantity of expense. So there's huge learning opportunity that is, as we're learning, fairly transportable, especially for those like Hadley, like Chris Miller, Brad Prudell, who are setting up these smaller trainer type units that don't even require a main air handling system. And I think that's really fantastic. I cannot wait to see the results of those. So.
Hey, Robert, I just want to make a comment about those alternate methods that those three are doing. It also provides a really good opportunity for our students to make them up and learn a lot about air handlers, pressurizing a duct, and other factors that they don't get just simply by working on a unit that's already made up and ready to roll. So it brings in a lot of other learning opportunities for them.
Absolutely true. And whether the programs decide to include those as part of the BAS program or to separate them out as a separate portion of their HVAC program, both could be extremely beneficial to each group. So yeah, that's fantastic. And a very good point, Ted. Thank you.
I can also see those ending up as a lot of small labs, learning opportunities that you could basically network, share, and plug into any class that they want to plug it into. You know, for me, it'd be plugging some of those into the basic HVAC classes versus the controls. And or if you're just teaching controls alone, you can still bring it in there so people get a basic of it. So it's a lot of learning opportunities with those.
Absolutely. Absolutely true. So, control a building. And I would be doing you a disservice by lying to you and telling you that they are. And even within a building that's primarily controlled by variable air volume, there are still other options that we can employ. Heat pumps, water source heat pumps especially, are becoming massively popular in the Midwest at least. And I think other parts of the country as well, especially those that are heading more towards electrification for their heating sources versus the combustion fuels. Fan coils are another very common tool depending on or in various parts of a building. If you have an isolated section that you don't really want to run the ductwork from the main air handler, things like electrical rooms that need to be isolated due to fire risk, mechanical rooms will often install devices that are fan coils, which are basically a miniature version of an air handler. oftentimes with hot water and chilled water coils, sometimes with outside air, sometimes with just return air. But they do have their own dedicated fans. Typically speaking, until you get into really big fan coil units, they will only have a supply fan, however. So those are another opportunity from an educational standpoint that maybe we'll get into one of these days. Cooling towers and fluid coolers. So when we get into the production of chilled water, or when we get into cooling off heat pump loops, cooling towers and fluid coolers are a frequent choice, especially when you get into large loads within your building. Because we really don't see big chillers. We're talking, 500-ton chillers. You don't typically see those with a DX type cooling coil, direct expansion of the refrigerant, because the cost is just prohibitive. So we set up a secondary water loop to carry the heat away from the chilled water or the chiller, and we cool that water off through cooling towers or fluid coolers. And yes, there is actually a difference between those two devices. They aren't just words used differently within different areas. Ask me about it sometime if you want a longer rant. Also, boilers aren't the only way we can make hot water. Heat recovery chillers are, again, one of those items becoming progressively more and more popular within various parts of the world. Using what would typically be considered waste heat from chilled water production to heat up water for the building. This can be heating water, this can be hot water for sinks and dishwashing and all those kind of things. It depends on how it's used within a building. And like I said, again, these are becoming more popular as time goes on, and are more common within larger and larger systems. Big hospitals like them, large schools sometimes like them. That's kind of hit or miss, but the more complex a building is, typically the more likely you are to see a heat recovery chiller, at least in my experience. Exhaust fans definitely show up in almost every building, if for nothing else than bathroom exhaust. They don't typically get their own control, though depending on what they're doing, they may. They may be based on schedule, they may have a rotary time clock on a wall, or they could be a extremely advanced negative pressure HEPA system for isolation rooms in a hospital, or chemical hoods. The applications for exhaust fans is a presentation all in of itself. So, and anytime we exhaust air out of a building, especially in quantity, we have to make it up somehow. Makeup air units are frequently, or sometimes called makeup air handlers, are usually a full outside air only unit. That whole goal is to we need a certain amount of air changes. You can even see smaller or larger fan coil units used as a makeup air unit in effect. Yeah. So, and this is just a sampling. The amount of equipment that we have within any given building is massive. Even for fairly straightforward buildings, the variety of solutions that we run into are very significant. At least in our area, a few years ago, the code changed for elevator mechanical rooms, and they required a completely dedicated cooling system that was not reliant on any other part of the building system. So a lot of people ended up changing over to mini splits for that purpose. If you get into data centers or even large networking closets, oftentimes they will have their own dedicated systems as well, crack units, computer room air conditioners. So trying to fit all of that into a single presentation isn't going to happen, but kind of catch it on the high level at least. So, questions so far?
I'm not seeing any in the chat either, Robert.
All right. Well, all of these systems are great, but, you know, as our friends the Jedi will tell you, control. We must have control. So how do building automation systems fit into this picture? So oftentimes, large equipment within our systems will have one or more controllers dedicated to it. Oftentimes, these are referred to as plant controllers. And this is kind of a general or generic category of controllers across multiple brands. And it just means that they have a significant number of inputs and outputs, somewhere typically in excess of 10 inputs and 10 outputs. That's not a hard and fast number, but kind of a general guideline. And depending on the control product line, it may use expansion modules to get to that input-output count. It may bridge across multiple controllers to do it. There are about as many ways to get to a plant controller as there are companies making controls. So, and these large pieces of equipment are things like chiller plants, boiler plants, or air handlers. Depending on the size of the plant, you actually don't necessarily have a lot of inputs or outputs tied up with a specific piece of equipment, more inputs than outputs usually from a monitoring standpoint, because most of our modern chillers and boilers come with their own control system, either built into the unit or overseeing multiple units. Air handlers, on the other hand, unless they have factory controls, have a massive number of data points that we are monitoring and or controlling. So they are often one of those that get larger plant controllers installed. Smaller equipment like our VAV boxes, like heat pumps, fan coils, get single controllers. These are often referred to as unitary controllers. And typically these are smaller. They're cheaper controllers. They may have less bells and whistles than the plant controllers. Sometimes they have exactly the same number of bells and whistles. And then of course we have miscellaneous pieces of equipment. We have dedicated control systems. You may control multiple exhaust fans out of a single unitary controller, or they may piggyback on to whatever controller is convenient and handy. Whether it's a plant controller for your mechanical room, or it may be just a VAV that serves that same area. Science lab, when we've got a general exhaust fan for a lab and we're already controlling the zone using a VAV, if we have extra inputs and outputs on that VAV controller, we'll very frequently use those to control an exhaust fan. So while this isn't the topic of our discussion this week, control systems, part and parcel to them is that they communicate. Most control systems will use multiple types of networks at this time. MSTP, which is a two-wire twisted pair communication, is exceptionally popular still. It's been around since serial communication started, basically. We're talking 50s, 60s level technology here. ArcNet is not as popular as MSTP or any of the others. I think there are only a few companies left that support ArcNet, actually. ALC, Automated Logic, being one of them. It's kind of their backbone for communication with their plant controllers, and they implement it very, very well. Ethernet and IP-based communications, network communications, or what we think of as modern network communication, and even wireless networks are definite possibilities within a system. Now, these are the media that they use to communicate. It's not the language that they use to communicate. That's what we call a communication protocol. Here in the US, the most popular at this juncture in time are, as the leader, BACnet, which is the communication protocol that was designed by ASHRAE. There are a number of manufacturers that are still in business today that were part of the pilot group that helped build BACnet. Delta Controls and ALC are two of them that I can think of off the top of my head. And BACnet is a fantastic protocol. It's a common language, so even your manufacturers that make factory controls for their air handlers or chillers, like Trane or Dakin, their systems may talk BACnet. So it's an easy integration with your system. Now, BACnet especially is a whole conversation. We're planning an entire workshop focused around BACnet at this time. So don't think that it's a light subject. BACnet is extremely heavy topic to get into, and there's a huge amount of misunderstanding about what BACnet is and what BACnet isn't within our industry. Also still very popular in the US is LAN communication, or Echelon. It, I believe, is still the most popular climate control communication protocol in Europe. Originally designed for the smart kitchen so that your toaster could talk to your refrigerator, amusingly. But there are massive amounts of LAN controllers installed all over the world, but a huge number in North America. For a long time, LAN was actually the leader before BACnet took over about 15 years ago or so. Modbus is also a very common protocol here, well, all over the world. Modbus you'll run into as direct communication with boilers, power control systems, computer room air conditioners. These types of systems love Modbus. It is a very low, easy to implement, very reliable communication protocol. Not super user-friendly from the configuration standpoint. There's much more work associated with it than there is with BACnet or LAN. And then we also have proprietary communication protocols. These are the communication protocols developed by a company, like Trane or Johnson Controls or Siemens, so that their controllers can talk to their controllers. We are getting away from these, and we have been for a number of years, thankfully, because they're very hard to work with other systems. So if your Trane branded air handler doesn't talk BACnet or Modbus or LAN, and it only talks Trane, then it's very challenging to trying to get it to play with a system, a control system that isn't Trane. And for a long time, it was one of the methods that companies used to kind of lock a customer into, well, you bought our controls, you initially spent, you know, hundreds of thousands of dollars installing our control system, and now you're stuck with us because Are you going to repay to install a whole new control system and rip ours out? That's a huge investment that's really challenging to justify. But like I said, we've been moving away from those. But the number of proprietary protocols out there is ridiculous. Many of the companies, big companies like Johnson and Trane and Siemens, have multiple proprietary protocols that they have developed over the years, different generations or whole new reworks of their communication systems. Sorry, got off a little bit on that one, but communication is a really big portion of the controls industry, integration especially, getting different systems to talk to each other and play nice. It is a hugely complex task. So within a given building automation system, typically your smaller controllers, so this could be anything from your unitary controllers like VAV controllers up to possibly including your plant controllers, will talk to building controllers. Sometimes your plant controllers double as a building controller or a middle management type controller, handling communication between your VAVs and the main building controller. But they pass up information to these building controllers for further processing, doing things like logic based around alarms, emailing alarms, texting alarms, calling alarms. Even in older systems, you could actually directly print alarms to a physical like laser printer. Graphical displays, that user interface aspect, especially in climate control systems. This is amazingly useful. Being able to look at a given floor or portion of a building and just kind of glance at it and see that everything is okay is amazingly useful from an operator's standpoint. And when you get into plant controls, chiller or boiler or air handlers, most people get a lot more information from looking at a graphic, a representation of that system, than they do trying to look at code or just inputs and outputs. Think about trying to analyze a spreadsheet versus looking at a graphic that shows you your airflow directions and everything. That's been something that's developed mostly within the last 20, 25 years. As our systems advanced, back before we did electronic controls or DDC, direct digital controls, many of our, especially our climate control systems were pneumatics, and we had very little visibility into the system. If we wanted to know what an air handler was doing, we walked over to that air handler and looked at the gauges that were built into it, or took out our temperature probes and analyzed the system from that standpoint. So we've come a long, long way. And one of the last things, and arguably one of the most important things that a building automation system typically does, is records what is happening with the system, referred to as histories or logs or trends. Amazingly useful to see and visualize long-term problems, or trying to find the root cause of an issue or the start of an issue. Just fantastically useful. Also great when you're trying to do energy calculations for remodels, changing your sequencing. You can look at the data and figure out what is currently being used with a little bit of additional work. Without those histories, it's really challenging to accurately predict things like return on investment for system upgrades. But when you can do that, when you can show the degradation of a piece of equipment over time and kind of predict the point at which it's going to cost more to continue operating a piece of equipment versus replacing it, it is really a useful tool for building owners, building operators, and technicians. So that's the end of my presentation. I know we covered a good chunk of information, and tomorrow we're going to get into programming very specifically and rather heavily. So I'm sure we'll run into a lot more questions then, and I've got some more presentation material specifically about why we've chosen what we've chosen for that period. But I'm not gonna melt your ears today and then again tomorrow. Tomorrow is going to be a lot more and a lot of doing while we talk about it. So, but that's kind of a, I don't know, 10,000, 30,000 foot overview of some climate control systems, some building automation systems, things like that. So I know we covered a lot of information and you were all really quiet throughout it. I think the mute buttons probably have something to do with that, but please pass up any questions that you've thought of.
I don't see any in the chat yet, Robert.
Thank you.
I think everybody's just anxious to get into the wiring part and knock that out.
That's fair. For those, especially our mentors or anybody who has anything, do you have anything specifically you would like to add? I think you were right, Ted. I think they want to get to it.
I just think it's critical that folks really start to understand serial networks and how you can convert them into IP networks and that down the road.
Yep.
That's probably one of the biggest issues that most people have is communicating with these devices, and a lot of it's serial. So whether you like it or not, you got to figure it out. So kind of what I wanted to, I think that's one of the most misunderstood things in BAS, that integration piece and everything else.
I absolutely agree, Bob. And it's one of the most challenging for people to grasp, for us to teach, and because, I mean, they're complex. No two ways around it. Serial networks especially are ridiculously complex. And trying to set up interactions between multiple systems is not a trivial task.
Yeah, and the worst part is in the instruction sets, a lot of the times you have to actually get to some factory direct person to understand to grab the actual like Modbus points or anything else, which is ridiculous. It should come with every single manual. So the spoiling controllers, all of them are like that across the board. So, yep, not the easiest thing in the world.
No, really isn't. And that's why we are planning an entire workshop, multi-day workshop specifically targeting those issues. So hoping that we will get to do that in person next time.
Forgot to say.
What was that, Bob?
Forgot to say in Hawaii.
There you go. In Hawaii. There we go. All right. I am going to share the wiring diagram real quick for the FW controllers, just to make sure everybody is at least a little bit familiar with it before we get into it. Our next step in the process for today is we're going to catch a stretch break here in just a couple minutes. And then we're going to break out into our groups and do some wiring. Now, just to make sure, make sure you have the latest wiring diagram. We discovered last week that there was an error in the diagram that we had posted from a while ago. So if you have not downloaded the fresh wiring diagram since Friday, Ted sent out an email about it. Melissa sent out an email about it. It was included in the email for this specific meeting. So if you don't have the latest version, if you even question if you have the latest version, please go get it off the Google Drive, please, please. Because the issue that was discovered was that we had the way I drew it, there was a direct short. Most of the time this won't damage your controller, but sometimes it will. So be aware, make sure that you've got the right version, and don't just follow the directions because that's what they say. Put some thought into this. Just because somebody drew it doesn't mean they were right. Everybody makes mistakes. Just a fact of life. If you're doing stuff, you're going to make mistakes. So.